Around 2,500 years ago, ancient Greek thinkers believed that the universe was one large, unchanging whole. They thought that all matter, objects, and substances were part of a single, connected entity. The idea was based on pure reasoning rather than physical evidence. One thinker, Democritus, challenged this view by introducing a new concept. He thought that everything is made of tiny solid pieces called atomos, meaning indivisible. Democritus proposed that matter is not continuous but made up of countless atomos that are always moving and combining in different ways. He believed physical changes occurred when these atomos separated and rejoined in new arrangements. He also claimed there were many kinds of atomos with different shapes, sizes, and weights. According to him, these traits were the only differences between atomos. Other features, like color, taste, and texture, Democritus argued, were not built into the atomos themselves but resulted from how they interacted and grouped together. Despite the originality of his ideas, most Greek philosophers rejected his theory because it didn't align with their belief that thinking alone could uncover truth. Since experimentation and observation weren't part of their approach, they didn't try and test or prove their ideas. As a result, Democritus' atomic theory was largely ignored for centuries. It wasn't until much later that scientists began to recognize the value of his ideas and build upon them with evidence. Plato shared his own version of atomism in his dialogue Timaeus. He believed that all matter, earth, air, fire, and water, was made from tiny, unbreakable triangles. These triangles could combine in different ways to form the four elements. This helped explain how one type of matter could transform into another. Unlike the common idea of atoms as round nowadays, he saw them as sharp, geometric shapes. Aristotle noticed the connection between Plato's theory and that of earlier atomists like Democritus. However, he strongly disagreed. Aristotle believed that matter was continuous, with no tiny particles or empty space, and that change happened when matter became what it had the potential to be. In 1803, John Dalton, a Quaker from Manchester, England, envisioned atoms as tiny, indivisible spheres. He proposed that each element consisted of identical atoms in size and mass, which combined in fixed ratios to form compounds. While studying gases, he observed that when two gases exert pressure, the total pressure exerted was the sum of the pressures from each gas. Since gases can mix without altering their properties, he inferred they must be composed of small, invisible particles. Extending this idea, he suggested that all matter was made of such particles. He also theorized that different states of matter, solids, liquids, and gases, had distinct types of atoms that couldn't mix with each other. In 1897, J.J. Thomson, a chemist from Manchester, discovered that atoms contained even smaller, negatively charged particles. He demonstrated this by directing a cathode ray, a beam of electricity, through a vacuum tube. When magnets were placed nearby, the beam bent toward or away from them, depending on their charge. From this, he deduced that the beam consisted of tiny, negatively charged particles, which he named electrons. Since electrons were smaller than atoms, he concluded that they must be components of the atom. He proposed that because atoms were neutral, he thought they were made of a positively charged substance with electrons embedded throughout, like plums in pudding. A stark contrast to Dalton's solid sphere model, as it revealed atoms had internal structure. In 1911, Ernest Rutherford, a physicist from New Zealand, discovered through his gold foil experiment that atoms have a small, dense, positively charged center, which he called the nucleus. He fired a beam of positively charged alpha particles at a thin sheet of gold foil and observed their behavior. Most passed straight through, indicating that atoms are mostly empty space. However, some deflected at angles, and a few bounced straight back, revealing that most of an atom's mass and all its positive charge were concentrated in a tiny nucleus. He concluded that negatively charged electrons must orbit the nucleus, held in place by electrostatic attraction, with their motion preventing them from collapsing into it. In 1913, Niels Bohr, a Danish physicist, expanded atomic theory by proposing that electrons move in specific orbits around a nucleus, influenced by wave-particle duality. This idea was supported by experiments like the double-slit experiment, which showed that electrons behave as both particles and waves. When unobserved, the places that they landed formed an interference pattern like waves. When observed, they behaved as particles, striking the screen in distinct spots. Applying this to atoms, Bohr suggested that electrons' wave-like nature confined them to specific energy levels. He proposed that electrons orbit the nucleus in fixed shells, where only certain wavelengths could form stable standing waves, explaining why electrons remain in defined orbits. His model also explained energy absorption and emission. Electrons jump to higher orbits when absorbing energy and release light when falling to lower orbits. This explained the discrete emission spectra of hydrogen and deepened the understanding of atomic structure. Bohr's work linked quantum behavior to atomic properties, laying the foundation for modern quantum mechanics and transforming how scientists viewed matter at its smallest scales. In the early 20th century, Erwin Schrödinger, a physicist from Vienna, Austria, advanced atomic theory by developing the quantum mechanical model, building on wave-particle duality. Unlike Bohr, who described electrons in fixed orbits, Schrödinger proposed that their exact locations were uncertain. Instead, electrons exist in probability regions called electron clouds rather than on precise paths. His model, supported by spectral and chemical evidence, introduced 4 quantum numbers to describe an electron's energy, shape, orientation, and spin, refining atomic theory. It also explained the periodic table structure, as electron configurations determine elemental properties. Schrödinger's famous thought experiment, Schrödinger's cat, illustrated quantum superposition, the idea that a system exists in multiple states until observed. His work laid the foundation for modern quantum physics, influencing fields like chemistry, electronics, and quantum computing. By treating electrons as waves and using probability to describe their behavior, Schrödinger redefined atoms as dynamic quantum systems rather than rigid structures. The quantum mechanical model remains the most accurate representation of atomic behavior. Finally, thank you for coming to this presentation, or watching this video. I am very happy. I spent a lot of time on this, but I think it turned out well. So, I'm going to need you to like and subscribe to the YouTube channel that I don't have, and this isn't going up on. Is that enough effect for you? Good.